Who's that boy? Who's that boy? It's Evan. We're back. Day 2 of the area between curves. Area betwixt curves 2.0. I'm just going to go through 2 examples and then I'll be done. I've posted extra notes to this because I had a big whoopsie and I actually recorded videos for the first 2 sections and I forgot I had the microphone on, so I had to re-record both of these. But I'm saving the notes from those so you guys have notes to reference, which are always good. So you can reference those notes if you want, and that's why I'm going to be going through fewer. Not too much today because you guys don't want to listen to me. You want to get your homework done. But we'll just do 2 problems and then you guys can be on your way. So first problem. Example. This is from the book. This is example 6. What a good number. 6. Find the area of the region completely enclosed by the graphs of the functions. And we have f of x here, given by x cubed minus 3x plus 3. And we have g of x here, given by x plus 3. And once again, this is a problem where it has not given bounds. The x bounds are not given. So we find them. And you can either find them graphically or algebraically. I actually don't think the algebraic version is too hard, but it's always good to graph these first 2. So let's draw a graph. It looks like that. I didn't do a great job of it. And then it looks like that. And really didn't do a great job because these regions are supposed to be the same size. So maybe I'll try to fix that for you all. I know you're going to appreciate me forever if I try to fix it. Okay. Alright, now they look closer to the same size. So this one's f of x, and this one is g of x. And so the area here is going to be this. Coloring on the iPad. Coloring on the iPad. So here's something really special, and I want you to get used to because it's super important. It's not super important. It saves you a lot of time. Like, I've used this so many times on exams and like just gotten problems right away. Or it's a lot easier to do it. So total area here. I'll write this in crayon. Total area is going to be twice the area of one of these regions. Oh, I want to stay in crayon. It's twice the area of one of the regions. By symmetry. So you can save yourself a little bit of hassle if you recognize that early in problems. You don't always have to do it, but yeah, it just saves you some time. So we really care about those intersection points. And so let's find them algebraically. And we talked about how to do this on the last problem. This is f of x equals g of x, solve for x. In this case, f of x was x cubed minus 3x plus 3, and g of x was simply x plus 3. So let's solve this for x, subtract x from both sides, we get x cubed minus 4x, and subtract 3 from both sides equals 0. Factor out a single x here, I get x squared minus 4. And x squared minus 4 is one of those beautiful quadratics called a difference of squares. You've probably heard the term. X minus 2, x plus 2 equals 0. So x equals negative 2, 0, and 2 are. If I scroll up, look at that. X equals negative 2, 0, 2 are intersection points. This is really negative 2 comma 0. This is 0 comma 3, and that's 2 comma 5. So there's our intersection points. I'm going to use this. I'm going to use this piece here. Total area is twice the area of one of the regions by symmetry. So I'm going to use that to my advantage. You don't have to if you don't want to. But I'm just going to look at the region on the right. So total area, TA, is 2 times the region on the right. This is top minus bottom. dx, the area on the right was from 0 to 2, you'll remember. Those are the x values there. The x value of the area on the right is 0 to 2. And the top curve there, well, it's the straight line, right? The top curve on the right side is the straight line. Which one is the straight line here? X plus 3 or x cubed, blah, blah, blah. It's definitely x plus 3. And I'm going to subtract the other piece. So there's top minus bottom for you. And then we end up with, let's simplify. I can't stress this enough, you guys. Simplify what's inside the integral. So let's do that. The amount of times that you're going to save yourself by simplifying what's inside the integral is too often. So we simplify that. What do we get? We get 2, the integral bounds are still there. What do we get instead? We get negative x cubed. We get minus 2x, and we get plus 3 minus 3 is just going to be 0. Oh, sorry. Negative x cubed plus 4x. Of course, this should be similar to what we had before. Plus 4x. Don't want to make the silly mistakes. Plus 4x dx. Okay, so 2, I can integrate negative x cubed with a power rule. It's negative x to the 4th over 4. And 4x with the power rule is just 2x squared. From 0 to 2, plug in 2. Negative 16 fourths. Plus 8 minus plug in 0, 0 plus 0. 16 fourths is negative 4. Negative 4 plus 8 is 4. 2 times 4 is 8. Happy day. So check with the book. Look, the book got an answer of 8. Look at that. We did it right. So there you go. It's a nice answer. If you wanted to do it without doing the 2 times the total area, just remember that you have to flip f and g around at each point in time. You would end up with probably an area of 0 if you forget to do that. So don't forget to do that. Obviously, areas are positive, so you should always get a positive answer. I'll write that down right here. You should always, no more caps. You should always get a positive answer. else you did something wrong. So if you don't get a positive answer, I would redo the problem. That's the way you want to think about it. Okay, so let's just do the next. Let's do one other problem from the book. Yeah. Okay, so this is exercise 4 from really like the exercises section. Exercise 4 from later in book. So this is, I don't know what to call exercise 4 later versus exercise. I guess it's called an example versus an exercise. So this is exercise 4. So let's find the area of the shaded region. Seems a bit shady to me, I don't know. You guys hate me. Okay, so here's our function. It's funny looking. It does this. It's supposed to go through the origin, it's fine. There you go, it goes through the origin. This function is y equals 2x divided by x squared plus 4. And then it gives me my region. X equals -1, and then the region all the way up to x equals 2. So I'm going to shade that in for you now. And basically, this is pretty standard stuff. We just want to keep in mind this piece needs to have a negative sign. Right, so if it's the area of a region under the x-axis, you put a negative sign in front of it because the regular integral would give you a negative number out of it. And that's not what we want here. So we're going to give a negative sign to that piece. So you'd either write it as integral -1 to 2 of this piece, 2x over x squared plus 4. We could either write that with absolute value signs, like I did yesterday, or we can split it up, -1 to 0, because that's where it changes from negative to positive. -1 to 0, 2x over x squared plus 4, and this piece, bam, has a negative sign. 0 to 2, 2x, x squared plus 4 dx. And, Yep. So now each of these is pretty easy to integrate. Hopefully you guys can look at this and decide what sort of integration rule we should use here. We really only have one choice. It's either power rule or use substitution, and it certainly doesn't look like a power rule to me. So this is use substitution, and then we go through our priorities list. So priority number 1, use substitution, is the natural log. Is there any natural log? No. Priority number 2 is the denominator. And is there a denominator? There sure is a denominator on these. So we are going to let, by priorities, u equal x squared plus 4, so that du equals 2x dx, and we have exactly what we wanted to have for du. I did that wrong. Here we go. So we have exactly what we wanted for du, and we have exactly what we wanted for u. And so both of these problems turn into one over u du, 1 over u du. And so this is really negative natural log of u plus the positive natural log of u. I'm keeping them separate. You can't actually add these together right now, right? Because these bounds exist. So really the lower bound here is 1 squared plus 4. This is 5. This is 4. This is 4. And this is 8. So that means this piece is, I realize I'm doing this fast. This is 5, 4, 4, 8. Or in terms of x, if you don't like changing your bounds on u in terms of x, this is x squared plus 4. This is an x from negative 1 to 0. That was the negative piece in terms of x squared plus 4. This one was from 0 to 2. So now we just calculate this out. Negative natural log of 4 minus negative natural log of 5 plus natural log of 8 minus natural log of 4. You'll notice that I have two negative versions of the natural log of 4, but thankfully I have other pieces that keep me positive. So I really have natural log of 8 plus the natural log of 5 minus 2 natural log of 4. We can use our log rules to simplify this if we want. This is the natural log 8 times 5 times 4 divided by 4 squared. Because natural log rules are kind of nice. So that's the natural log of 40 over 16, or the natural log of 10/4. And so yeah, we still got a positive answer even though it doesn't quite look like it. Anyway, that's all I had for today. Go ahead and look at those other sheets. I'll make sure I write that down here. There are extra PDFs if you want extra stuff to look at. I guess I'll see you tomorrow, and it's a pretty exciting topic, and it's our last section of the year, so get excited. Bye.